Hello, this is Robert Falkenberg. I am a research assistant at the Communication Networks Institute at TU Dortmund University. And today I will present you FALCON, an accurate real-time monitor for client-based mobile network data analytics. Let's start with the scope and the contribution. The research is conducted in the Collaborative Research Center SFB 876, which is about big data on small machines, in particular in resource-efficient and distributed platforms for integrative data analysis. The work presented here is part of the work package 2, Modeling of Heterogeneous IoT Environments. And the greater goal is to enable resource-aware and resource-efficient communication for the Internet of Things to increase battery lifetime, reduce network congestions, and the underlying research question is, what are the potential benefits of resource-aware communication? And finally, how to obtain the necessary information. Imagine we want to implement a resource-aware network selection in a 4G or 5G cellular network, where we have 3 networks available and we want to perform our transmission as efficiently as possible, which means we want to perform our transmission as fast as possible. So what is a suitable metric to select the most appropriate network or the most promising network for our pending transmission? Well, first of all, we could use a previous data rate, but we have no information about the data rate which can be achieved in the other networks. We could perform some kind of probing, but on the other hand, this would waste resources in the other networks and in the user equipment as well. We could start a simultaneous transfer, but this would waste even more resources. So some kind of forecast and prediction is required, which is obtained just from observing the activity in those networks. Which options are available for data rate prediction? Well, in an ideal world where the base station has a very complete information about the activity in its cell, the cell could just broadcast the expected data rate of an additional user over broadcast channels, so the user equipment could very easily decide which link to choose to perform its transmission as efficiently as possible. Well, or at least in a nearly ideal world, the base station could at least broadcast the number of currently active users in the cell, so we could at least get an information about the general activity in the cell, and we could divide the total available data rate by the number of currently active users. However, we are in reality, and in reality the base station explicitly assigns resources to the particular devices in the cell at a subframe basis with a resolution of 1 millisecond. And a caveat on this is that by design these assignments to the single users are only visible by the addressee and not by the other devices which are also in the cell. So the main challenge is to extract those resource assignments of all active users in the cell. To discover the resource allocations of all users in the cells, we can perform control channel analysis. And this is what FALCON does, which is an acronym for Fast Analysis of LTE Control Channels. It is a software-defined radio approach which can be run on a regular computer, and it discovers every resource allocation for every active device in real time. And it works in public LTE networks and even without a SIM card, so no attachment to the cell is required to run this application. Let's have a look how resource assignment works in LTE. LTE has a resource grid which is divided in time and frequency, and it's structured in subframes of 1 millisecond and resource blocks with a frequency bandwidth of 180 kilohertz. And such a unit forms a resource block, which is the smallest assignable resource unit which can be assigned to an active device active in the network. There are a couple of channels in the resource grid which are located at specific locations in the time and frequency grid. And at the beginning of every subframe there is the PDCCH, the physical downlink control channel, and this control channel contains the resource allocations for the current subframe. So it can be seen as a data structure containing pointers for the single devices, which resource blocks belong to which device. So our approach is, let's decode the PDCCH and reveal all the information in this channel so we get a very complete overview of the resource assignments and the overall activity in the cell. How to decode the PDCCH to get the resource allocations, which are also known as downlink control information, or DCI. First of all, the PDCCH is structured in control channel elements, where the actual number of those control channel elements depends on the cell bandwidth. Each of those control channel elements has 72 bits, which are encoded and rate-matched bits on the channel. To decode the information, first of all, we have to perform some rate unmatching. The rate unmatching has two inputs. First of all, the aggregation level, because the base station can decide whether to aggregate 1, 2, 4 or even 8 consecutive CCEs to increase the redundancy of the DCI information and ensure a proper decoding even for cell edge users. The second input depends on the DCI format, where different DCI formats have different lengths, and the actual DCI format used by a device depends on its transmission mode. Actually, a normal device has perfect knowledge about its current transmission modes, so it just has to look for the matching DCI formats which belong to this transmission mode. However, we are an independent observer and we have no idea about the currently active transmission modes of those data. Unfortunately, the PDCCH has no table of contents, so we have to consider all of those combinations which can be selected from here. And each of those combinations has to be decoded by a Viterbi decoder and results in some bit sequence, whether it is true data or corrupted invalid data. So we have a lot of potential downlink control informations and we have to decide which of those are true. Actually, each DCI is protected by a cyclic redundancy check, CRC checksum, so it can be validated in this way. However, the CRC is scrambled with the radio network temporary identifier of the addressed device. So a normal device knows its own RNTI and it can check the checksum whether the resulting checksum matches to its current RNTI and decide whether to use this DCI information decoded or to discard it. We as an observer have at the beginning of our observation at least no information about the set of currently active RNTIs, and unfortunately finally we have no possibility to decide which of those potentially decoded DCI are valid because we do not know the CRC or the RNTIs. So at the same time when we start looking on the channel to decode the PDCCH and get the resource allocations, we have to bootstrap the list of active RNTIs somehow, which is one of the most difficult parts in this approach. In the literature, several techniques for DCI validation and discovery of valid RNTIs have been published. This table gives an overview of the key methods used to achieve this goal. LTI, for example, re-encodes each decoded candidate and compares the encoded sequence with the received channel bits. If the sequence deviates by more than a few bits, the DCI is discarded. However, we will see later that this approach is very sensitive to noise and leads to lots of false detections. OWL, on the other hand, extracts the RNTI assignments from the random access response, which is transmitted by the eNode B when the UE becomes active or joins the cell, for example by a handover. This works well for long-term observations, but it does not detect the RNTIs of users who were already active at the beginning of the observation. For such cases, OWL falls back to the re-encoding approach of LTI, with all of its limitations. In our previous approach, C3As, we keep track of all potential RNTIs that come from the decoded DCI candidates in a histogram. Only those RNTIs are accepted whose frequency in the histogram exceeds a threshold value within a time window of a few milliseconds. Furthermore, since the DCI for an RNTI can only be located at specific locations within the PDCCH, any non-matching candidates can be safely discarded. This property is a result of the search space function, which is designed to limit the number of decoding attempts of a regular UE during DCI search. Finally, with FALCON, we introduce a new shortcut decoding approach, which almost instantly discovers active RNTIs upon their first occurrence. We will see it on the next slide. Let's take a look how FALCON extracts the DCI from the PDCCH. Here is an example of the PDCCH for one subframe, which consists of a number of control channel elements, CCEs. The gray ones are occupied by the actual downlink control information, and the white ones are unused and contain only the background noise of the radio channel. Note that not every CCE with a signal power above the background noise level contains relevant information for the current cell, because the PDCCH of neighboring cell overlap in time and frequency. Once again, since there is no table of contents, we do not know the DCI format and the aggregation level of the occupied fields. So we start to search with the highest aggregation level of 8 and inspect windows of 8 CCEs for any meaningful information. If a window contains any unused CCEs, the entire window is skipped without any decoding and the search continues with the next window. In this case, the first window contains empty field, so it is skipped, and the next window as well. If all possible locations for a given aggregation level have been processed, this search continues with the next smaller aggregation level. Of course, windows with empty or previously decoded CCEs are skipped. Now, in this example, we have a window of 4 occupied CCEs, which has to be inspected for DCI. The location is decoded for each possible DCI format with the use of the corresponding rate matching configuration. It is then checked whether the decoded candidates include DCI for already known RNTIs. Remember, the CRC checksum of a DCI candidate is scrambled with the potential RNTI of the addressee. In our example, it is assumed that none of the decoded candidates matches a known RNTI. So instead of going forward to the next location, we first inspect this particular window recursively with smaller aggregation level. The window is split into 2 halves with the next smaller aggregation levels, and those windows are inspected as described before. In this example, both windows contain a DCI for an RNTI which is already known, so the matching DCI are accepted and the overlapped CCEs are marked as checked, so that there is no further search required on those CCEs. After the recursive descent is completed, the next window with the previous aggregation level is explored. In this case, the following windows contains empty elements, so it is skipped, and the next one too. Now another window is processed, also with no matching RNTI after decoding it with all possible DCI formats. So again, we descend recursively and decode the first half of the window with the next smaller aggregation level. But this time we find one candidate whose RNTI matches to its parent counterpart at the higher aggregation level using the same DCI format. So, what does this mean? First, the unencoded raw DCI, including the attached and scrambled CRC checksum, would fit into a single CCE regardless of the DCI format. Second, the base station encodes these data structures convolutionally with a rate of 1/3 and applies a predefined interleaving pattern on it. For the most DCI formats, the encoded sequences fit into 2 of 4 CCEs without the requirement for puncturing. The leftover space, especially when using even higher aggregation levels, is filled by a circular repetition of the interleaved sequence. Conversely, this means that even a shortened sequence still contains enough redundancy to be decoded correctly, if the channel conditions allow for it, of course. However, this relationship only exists for the correct DCI format, since the interleaving pattern and the repeat point depend on the length of the DCI format. With the wrong DCI format, the encoded bits are misaligned by the de-interleaver, so that the result of the complete and the shortened sequence are different. Therefore, the existence of such a match is a very strong indicator of the correctness of the decoded candidate. Consequently, such candidates are accepted straight away and the corresponding RNTI is added to the active list for the future. This enables a reliable detection for DCI for unknown RNTIs upon their first occurrence. Once again, the overlapped CCEs are marked as checked. And the search continues, here with the next smaller aggregation levels. If the recursive search of a location results in no match at all, then all DCI candidates are discarded and their potential RNTIs are added to a histogram of uncertain RNTIs. The method is adapted from our previous approach, C3As, and serves here as a fallback for DCI which cannot be found by the shortcut approach, for example, in case of insufficient channel conditions. Now let's validate the accuracy of FALCON. To achieve this, we generate a well-known LTE signal with a specially developed base station mock. The base station mock generates a regular LTE baseband signal, including reference and synchronization signals, and encodes the PDCCH according to a DCI trace file, which was obtained from a real eNote B in a production environment in order to obtain a realistic and representative PDCCH occupation. Afterwards, a predefined noise level is added to the signal to simulate the influences on the radio channel. And the resulting signal is finally fed into FALCON to perform the DCI decoding and the RNTI discovery. The resulting output trace file is then compared with the ground truth from the input trace to measure the amount of missing and spurious DCI. In addition, we also decode the same signal with OL to evaluate the differences of both approaches. At this point, it is important to understand that this evaluation here focuses on the reliability and performance for the case of short-term observations over a few seconds. Consequently, the RNTI discovery is not based on the random access response, which is the most reliable approach for long-term observations, but instead on the shortcut and histogram approach of FALCON and the re-encoding approach for OL. The DCI trace file spans a time window of 1000 milliseconds and contains about 2500 allocations. Simulations were performed for different signal-to-noise ratios of the baseband signal, in steps of a half decibel by adjusting the noise level accordingly. After each run, we measured the total number of missed DCI, in other words, the number of DCI contained in the input file that were not detected by the detector. And we also measured the total number of spurious, false or phantom DCI which were not part of the initial input file. The average numbers of missing DCI are displayed as continuous lines, and the dashed lines show the average numbers of spurious DCI. Error bars represent the standard deviation of the displayed quantity, since each experiment was repeated 10 times. Note that the number of false detections is displayed in a logarithmic scale. For an SNR of 0 dB, which is a very poor signal, almost all DCI are missed by OL, while it produces hundreds of false DCI that were never transmitted by the base station. But even with a reasonable SNR of 15 dB, 50 DCI are lost, and 90 false DCI are detected instead. In contrast, with FALCON, the number of missed DCI is always far below the results of OL. And with an SNR above 8 dB, even less than 4 DCI are missed in average. But the most prominent result here is the constantly very low amount of phantom detections, even in case of a very poor signal. How do the systems behave in the field? For this purpose, we placed 3 instances of the FALCON recorder in line of sight on a location where base stations of 3 different network operators from Germany were located, and performed periodic short-term recordings of the raw LTE signals. Right after recording, the captured signals were decoded by FALCON and OL to extract the downlink control information. Each network operator provides a cell in band 20 at 800 MHz and a bandwidth of 10 MHz. But the measured signal strength and quality of the networks differ significantly, as we can see in the table. The differences are a result of the alignment of the antennas and the different output power of the respective base station. Finally, the location is next to a highway, which is densely populated during the rush hours, so we expect a high user fluctuation during that period. So, which accuracy can we achieve in the field? First of all, we do not have a measure for ground truth in the field, so we cannot measure the amount of missed or false DCI. But at least for the spurious DCI, we can define another metric, which provides a lower bound for the ratio of false detections. We can measure the fraction of subframes with contradictory resource allocations, which are impossible. For example, if the same resource block in a subframe is assigned to more than one RNTI. Such collisions are a reliable indicator that the decoded subframe contained at least one spurious DCI with an overlapping resource block allocation. In this table, we see the fraction of subframes with such contradictory allocations over all conducted measurements, divided by uplink and downlink for each mobile network operator. Especially in the downlink, we can see that FALCON clearly outperforms OL in terms of false detections. In case of poor radio conditions, we see a difference of 3 orders of magnitude. The large difference between downlink and uplink is explained as follows. First of all, today's networks show a higher utilization of resources in the downlink rather than in the uplink. So in the downlink, the probability that the spurious DCI with random resource allocation collides with another true allocation is much higher than in the uplink. Second, the spurious DCI appear with random DCI format and content. However, LTE defines only a single DCI format for uplink allocation, which is format 0, while the remaining formats are used for the downlink. So again, the probability that a random DCI hits the downlink is much higher than in the uplink. But remember, the actual number of false detections is higher than the number of collisions, because not every false DCI can be detected this way. Now we check the suitability of FALCON and OWL for counting the number of active users in the cell and draw further conclusions from the observed behavior. For this purpose, we take a look on the activity in the cell in the morning of a business day. The figure shows the number of detected allocations for each RNTI within a 5-second observation window in network 3. We can see a peak region of highly active RNTIs, which is properly detected by both FALCON, the blue circles, and OWL, the red crosses. However, an additional noise floor of red crosses uniformly spans the entire RNTI value range with a very small magnitude. It is very unlikely that these RNTIs are true, since the detections of FALCON are limited to the peak region and some additional reserved RNTIs at the edges of the value range, which have special purposes like broadcast, paging, and random access. If those RNTIs were true, one would expect FALCON to catch at least some of them. On the other hand, the false detections fit well into the picture we have clearly seen in the simulations before. Due to the large number of incorrectly active RNTIs, OWL cannot provide a reliable estimation of the number of active users in short-term observations. Furthermore, we can see that the peak region moves forward over time, which indicates that the eNode B assigns new RNTIs consecutively. Here we see the peak 5 minutes later, and further 5 minutes later. As a bonus, we can compare the speed of the forward movement with the number of random access procedures. We have seen that the highest RNTI value advances by 7,500 in 10 minutes. This corresponds to an assignment speed of 12.6 RNTIs per second. At the same time, in the observed cell, we detected in average 2.6 random accesses per second. Multiplying this value with the 6 sectors of the base station, with 3 sectors per frequency band, we would expect nearly 16 random access procedures per second, which overshoots our measurement. However, only 2 sectors of each frequency band point towards the populated highway, while the other sector point into a residential area. Taking only those 4 sectors for multiplication results in nearly 11 random access procedures per second, which fits well to the speed of the peak movement. We have seen these RNTI concentrations in various networks. However, some properties, like the wraparound value, seem to be vendor-specific. We have also seen that some cells have 2 peak regions. We assume that such eNode Bs might split the value range into 2 or more regions, or sections, where each section is associated with one of the frequency bands provided by the cell. In this case, the second peak would come from users who are primarily registered in the other frequency band and use the observed cell for carrier aggregation with the same RNTI. Again, this depends on the proprietary implementation of the base station. In the second example, we see how the number of active UEs changes over time. The figure shows the average number of active RNTIs, where each sample comes from a short-term observation over 5 seconds in network 2. Note that the measurement was conducted during the Easter weekend, with Friday and Monday being public holidays. We can see about 15 UE being active during daytime, while only about 5 UE were active during night. However, in the rush hours on Thursday and Tuesday, the number of users increased significantly. FALCON comes with a comprehensive GUI for live visualization of the cell activity, which is shown in this video clip. In the upper right corner, the GUI displays the spectral power density of the raw downlink signal of the observed cell as a spectrogram or a waterfall plot. Warm colors, like red and yellow, represent a high signal strength, while cold colors, like blue, represent a low signal power. In the current figure, we can clearly see the occupancy of the resource blocks, but we cannot distinguish the addressed users. The upper left corner, however, shows the detected downlink resource block allocations from the decoded DCI. They are mapped to the corresponding locations in the resource grid and are colored differently for different RNTIs. In contrast to the spectrogram, this view provides a distinction of the single users by their different colors. Furthermore, we can see a clear match of the resource allocations and the occupancy in the spectrum. In the same manner, the allocated resource blocks for the uplink direction are displayed below. Note that both figures on the left side are based exclusively on the PDCCH information, so they are independent from the radio conditions and the distance of the individual UEs. The remaining window shows the activity of single RNTIs in a histogram and overall statistics regarding the cell throughput, resource utilization, and modulation and coding scheme. Thanks to OpenGL acceleration, the views are drawn in real time. The display can be stopped with a click into a window, and the view can be scrolled back in time. Another click continues the real-time view. It can operate in live mode with an attached SDR or with a recorded signal, as shown in this example. For those who prefer the command line, we also implemented a text-based output with optional coloring. Occupied resource blocks are displayed as colored digits, which correspond to the last digit of the addressed RNTI. So let's summarize. Currently, network data analytics is an emerging research field, as it holds a large potential for increasing the quality of service and experience, the invention of novel methods for congestion management, like resource-aware transmissions and predictive network selections, in order to achieve higher throughputs and reduce the energy consumption of the mobile devices. We have seen that obtaining the necessary network information for research is a particular challenge. With FALCON, we provide an open-source, SDR-based instrument to close this gap. The novel shortcut decoding approach provides fast and reliable RNTI discovery, especially for short-term monitoring and for quick insights into the current load situation. Of course, FALCON can be used for long-term monitoring as well, for example to derive realistic UE traffic models, to detect peak hours, or to evaluate the spectral efficiency. Finally, a comprehensive GUI enables a quick and intuitive overview of the activity in the observed cell. And that's it. Thank you for listening to my talk and have a nice day. Goodbye.